Today we continue with the Steel Bridges from Concept to Delivery lecture series with this lecture 5. To remind you, the education packet is divided into 6 lectures. Last time we learned recommended details for splices, stiffeners, cross frames that are practical and economical for steel girder bridges. We also saw how bridges are fabricated and protected from corrosion by durable steels and protective coatings. Today we're going to go on to lecture 5. So for lecture 5, we start with that bridge designers, fabricators, erectors, and contractors have always been innovative in developing bridge projects for owners. In lecture 5, we will introduce some innovations that use modular designs for foundation systems and modular designs for superstructure systems for building bridges with what's called accelerated bridge construction, or ABC. Accelerated bridge construction has become an important part of the bridge industry in that it reduces on-site construction time and reduces disruption to the public, and it improves project delivery time and work zone safety. In this lecture, we will look at accelerated construction bridge products, innovative ABC bridge systems, and advanced ABC construction techniques that has changed the way bridges are built to meet the owners and the public's needs. Some of the case studies we will look at and some of the videos we will see will seem like marketing for particular bridge manufacturing or fabrication firms, as we mention their names and their products. And admittedly, it probably is. And if through my class they get business because of this, good for them. However, how we're going to look at these is we will consider that these case studies are options for the owner or the engineer when considering how accelerated bridge construction can meet their bridge needs. So from the Federal Highway Administration ABC website, approximately 1/4 of the nation's 600,000 bridges require rehabilitation, repair, or total replacement. However, the work that occurs from on-site construction activities can have significant social impacts to mobility and safety. In many cases, the direct and indirect costs of traffic detours that result from the loss of a bridge during construction can exceed the actual cost of the structure itself. For example, full lane closures in large urban centers or on highways with heavy traffic volumes can have a significant economic impact on commercial and industrial activities in that region. Partial lane closures and other bridge activities that occur alongside adjacent traffic can also lead to safety issues. Because of the potential economic and safety impacts, minimizing traffic disruptions is a goal that should be elevated to a higher priority when planning bridge-related construction projects. So now to the definition. Accelerated bridge construction is bridge construction that uses innovative planning or design or materials or construction methods or a combination of those in a safe and cost-effective manner to reduce the on-site construction time that occurs when building new bridges or replacing and rehabilitating existing bridges. Now for the applications in ABC. We will look at examples that lend themselves to accelerated bridge construction by starting at the substructure and moving up to the superstructure. In precast construction, the substructure is fabricated at an off-site precasting plant and shipped to the site. This shortens the on-site labor and construction time. With the high level of quality control attainable in a precast plant, high-performance concrete can be used. This results in more durable substructure units with higher quality and better finish. The higher strength of high-performance concrete also allows the use of hollow sections, resulting in material savings, lower hauling and erection weights, and decreased foundation costs. The use of post-tensioning with precast substructures will further improve durability by eliminating cracking under service loads and providing stiffer vertical elements that minimize deflections. Here, bridge pier columns can be prefabricated, brought to the site, and connected to the footing. Precast concrete bent cap beams, the picture on the right, are the most common prefabricated elements in bridge substructures. Bent caps are generally the most difficult elements to construct on site using cast-in-place concrete, where shoring and forming can be extensive. These have the benefits of the element being prefabricated off-site and only needing to be transported and installed on-site. Prefabricated substructure elements can greatly decrease the time of construction. Standard abutment construction at the ends of a bridge can be a long process. Therefore, prefabrication can provide an excellent opportunity to reduce the overall construction time of a bridge project. Advantages of precast concrete integral abutments are that they eliminate the bridge deck joints, which is a common area for water leakage and deterioration in bridges, allows thermal movement and girder rotation for the support. The soil forces are transferred into the bridge superstructure itself, reducing the size for the spread footings or multiple rows of piles. And they are quicker to construct than traditional abutments. Sheet pile wall abutments are constructed from hot rolled structural shapes with interlocks on the flange tips. These interlocks permit individual sections to be connected to form a continuous steel wall. Hot rolled sheet piles have several advantages when used in the design and construction of bridge abutments, with faster execution time than other alternatives. Steel sheet piles can be installed in advance of other works, and there's no excavation for the foundations required. And steel sheet piles have immediate load-bearing capacity. At the bridge end, many times there's a need for vertical walls or retaining walls. Compared to cast-in-place walls and their extensive foundations, modular precast wall systems such as the modular reinforced soil retaining and geosynthetic reinforced soil wall systems can be assembled and connected on site to create modular precast walls, as shown in the top left picture. The two common forms of this include mechanically stabilized earth wall systems and modular block systems. The wall foundations are smaller because the wall is tied back to the soil for the reinforced systems. And installation of this type of wall can progress rapidly because the system is built while the soil is being filled in behind the wall. So that's the substructure. Next, we'll move on to the superstructure, but we'll start with one that's called a buried steel bridge, which is kind of a combination of sub and superstructure. There are two kinds, corrugated steel pipe, which many call culverts, and corrugated steel plate, which is an arch type structure with foundations at each end. So for our first case study, this corrugated steel plate buried steel bridge was built on Route 2B in St. Johnsbury, Vermont. The bridge was fabricated and designed by Big R Bridge in Greeley, Colorado, and built by J.P. Sicard. The bridge is located on a steep, narrow site on a curve with residents living nearby. The soils at the foundations are poor, and the designer needed a system that could accommodate significant differential settlement between the left and the right side of the new bridge. Limiting the number of days the trail would be closed and constructing the bridge before the peak summer and fall seasons was a priority of the owner. The contractor had a maximum 50-day closure of the roadway above and a 28-day max closure for the trail that goes underneath, but the contractor earned a monetary incentive when it was reopened after just 45 days. This ABC project used precast concrete foundation blocks and precast wall panels to significantly shorten the construction time with no concrete curing times. So how do these things go together? There are curved steel corrugated plates that are shipped to the site, stacked and shipped to the site. They're bolted together at the site, and then light equipment can be used to lift the arches into place. They are connected together across the width for stabilization of the arch system. And then the bridge arch is covered with soil and the roadway built. This video shows how a single arch is lifted and placed on the foundation. Now I have to admit I sped it up 4 times because it really is a boring process. Here we see fairly small construction equipment erecting these arches is pretty simple and quick work. I do admit it's a pretty boring video to watch. So that shows one of the arches going up, and they just repeat that process, and then they cover it with soil. Sometimes they put a moisture barrier against the corrugations if the soil was reactive with steel. And the plates are galvanized, so they're protected well.
Barker?
Yes.
We couldn't hear what you were talking about in the last slide because of the video.
Oh, you couldn't hear me?
No, it was too loud. The video.
Okay. Well, what I more or less said was it's a really boring video, just showing a couple excavators picking up an arch and placing it on the foundation. And then you just pick up the next one and attach to it, and then you have yourself the arch, and then you just put soil on top of it and build the roadway on top. I'll try not to talk during the next, well, some of them don't have sound, so we'll see how that goes. But thanks for chiming in. So these buried steel bridges are lighter weight, flexible, and able to handle anticipated settlement better than conventional bridges. With the lightweight structure, they were able to use precast footings. And because of the arch, shorter spans are required to achieve vertical clearance requirements. And finally, there is a continuous road surface across the top with no bridge deck joints or joints to maintain. Plus, and this is a personal opinion, I think they are just really beautiful bridges. So next, here's an example where the choice of material itself met a need in the effort to replace a bridge in an emergency using accelerated bridge construction. Rain flooding took out several bridges in Buffalo County, Wisconsin, including the Sheps Valley Bridge, which connects a state highway to about 20 homes and production farms. The emergency replacement was in the winter months, so concrete curing would be problematic. Wheeler Bridge from Minneapolis, Minnesota, designed a steel-rolled bridge with timber decking and steel and timber substructure so that there was no need for concrete on the bridge. The bridge was then built by J.F. Brennan. The substructure was built with driven steel piles and a treated timber abutment. The superstructure was rolled beams with simple cross-frame diaphragms. A timber deck with an asphalt overlay was installed. And finally, a crash-tested railing system was installed. There was no concrete on the project. The project delivery was nearly 3 times faster than the Department of Transportation method of design, bid, build. The use of steel beams was a key component of the expedited project delivery. All components could be erected during an emergency during the cold winter months because no reinforced concrete was required. So traditional construction methods, but using or choosing the materials carefully so that it could be constructed in an emergency accelerated bridge technique. Staying with the idea of rolled beam bridges, modular rolled beam structures are a common technique used for accelerated bridge construction. Here in the shop, they put two beam elements together connected with diaphragms in the controlled conditions of the shop. They ship it to the site and they simply place it on the abutments. One option is to precast a deck to the modules, ship the units and place on the abutments, and use an ultra high performance concrete for a closure pour between the modules, between the deck part of the two modules. This is a rolled beam modular bridge built as a bridge replacement project for State Road 30 near Pittsburgh, Pennsylvania. The contractor was Brayman Construction out of Saxonburg, Pennsylvania, and the modular units were fabricated by Quality Bridge and Fab out of West Middlesex, Pennsylvania. The precast deck was cast on the modular units in the shop by Brayman Precast. The project included demolition of the old structure, replacing the abutment stems or walls, and the approach slabs, and constructing the superstructure with the modular units. And as you can see here, it says the bridge was replaced in 57 hours. And this included the abutment work and the approaches. The single span structure was replaced using accelerated bridge construction methods. Working 12-hour shifts, the old structure was removed and the new one installed in just 57 hours. The road was closed Friday after rush hour and opened Monday morning before rush hour. The beam sizes were W30 by 99s, 54-foot long with simple channel cross-frame diaphragms. You can see the joint that was closed with the ultra-high performance concrete closure pour right here between these two girders. The modular pairs were assembled, the deck was cast, the modules were shipped to the site and set. The ultra-high performance concrete was used for the closure pours. So this video shows, this is one of my favorite videos because it shows a great accelerated bridge construction project. There is no sound, so I can kind of explain what's going on while it plays. So they close the bridge and they bring in some equipment to start unstitching or unconnecting the elements of that bridge. They start tearing it down. They get it torn down while they're working on the approach, and then we skipped and they cleared all that out of there. Now they're fixing those abutment walls. They're raising them up, putting the bearing pads there. They've got the module and they lift that into place. They set it down, they connect it. Now they bring in the next module. While they're doing those modules, of course, they're working on those approach areas. On the right side, you can see they're putting in some approach slabs to get from the ground surface to the bridge. There comes another module. Next day, they're working on the left side. Now they've put the bridge in place and they're starting to put that ultra high performance concrete in those strips between the modules. They finish up that left abutment. They open one lane while they finish the other side. And then they open the bridge. Whoops, I think I started it again. We don't need to see that. So with careful planning, there was minimal disruption to the traffic. The old bridge was removed and the new bridge was ready for traffic in 57 hours. For that size project, for as much as they did for that project, that's a pretty amazing accelerated bridge construction example. Okay, moving on to another type of modular system called the press brake formed steel tub girder bridge. The Short Span Steel Bridge Alliance, which I am a part of, in fact, I was part of developing this, developed a new concept called a press brake tub girder for an economical steel bridge design that meets the needs for accelerated bridge construction. The idea of tub girders has been around for a long time, but they are usually built up larger structures with tub flanges and webs cut out separately from the plates and then welded together. The general idea of the press brake tub is that a standard width plate that we saw in previous lectures, either 72 or 96 inches wide, is bent by a press brake into a tub shape, maximizing its performance with no waste of steel material, and more importantly, no welding required. The tub can be pre-topped with a concrete deck and the modules shipped to the site and assembled with ultra-high performance concrete closure pores, and several have been built across the country so far. However, the example we will first look at is a special case of the press brake tub girder. This example press brake tub girder bridge was a replacement for an existing bridge in Muskingum County, Ohio. This bridge is special because the tubs are composite with a sandwich plate system deck that is less than 2.5 inches thick. The result is a low profile bridge that did not require extensive approach work, even though they were increasing the hydraulic opening for the crossing. Or in other words, they made the bridge longer so that there is less flooding potential. And because of the shallow depth of this system, they did not have to raise the approaches coming up to the bridge. And approaches are very expensive. The tubs were bent in a press brake by Mako out of Ellsworth, Kansas, and fabricated by US Bridge out of Canton, Ohio, with the sandwich plate from SPS North America out of Banks, Oregon. The steel was galvanized and metallized for long performance by AZZ Galvanizing. And so this picture here shows that they were built in pairs with the guardrail attached, literally just placed on the bridge. And since it was a steel deck surface, they were simply bolted together. So this kind of shows the process. The girders were bent in the press brake. Then they were galvanized. The sandwich plate is just less than 2.5 inches thick, made from steel plates, sandwiching a polyurethane elastomeric core. That is attached to the tubs. And then the tubs are loaded on a truck and shipped to the site. This video shows just how easy it was to install on the abutments. This one does have sound, so I will not talk through it. So yeah, I'm pretty proud of that bridge because that was one of the first installations of a design that I was part of developing. And then this is going to become more popular because a very large company called Valmont Industries is creating a whole division to where they will be able to produce these at low cost and sell them for, especially for county bridges. So this bridge was erected from one side due to the light weight of the modules in 20 minutes. There was excellent match fit and dimensional accuracy due to the shop fabrication and the sandwich plate quality. There was no concrete, so no curing time, and the bridge had immediate load carrying capacity once it was placed. And of course, the locals appreciated the 30-day road closure with the ABC modular bridge. Here are two other press brake tub girder bridge examples. The left bridge from Mercer County, Pennsylvania shows a skewed bridge, meaning that the ends abutments are not normal to the traffic way, with precast deck panels placed on top of the erected tubs with openings in the deck for grouting the tub studs to make the bridge composite with the deck. The right bridge from Monroe County, Michigan had precast decks on individual tubs fabricated in the shop and shipped to the site. The modular units were placed and closure pores connected the units, completing the superstructure. These two bridges were designed by Construct, which is affiliated with Valmont. That's the company that is creating a whole division doing this. And we will take a closer look at one of these bridges in Lecture 6, just because it's cool. So the previous case study showed bridge types and modular fabrication techniques that provided accelerated bridge construction. The lateral slide bridge construction technique is where the planning and construction method results in ABC. Here, the bridge is built on temporary supports, usually by traditional construction methods, next to the final bridge location, and literally just pushed into the final position. The offsite construction improves safety and traffic disruption is minimized to when the old bridge is removed and the new bridge is slid into place. The example we'll look at is the Interstate 44 bridge over the Gasconade River in Missouri. And it is an excellent example of the lateral slide construction technique. It's also a place that I used to go to all the time and fish. I used to fish under the old bridge. I have not been back to fish under the new bridge. The bridge was fabricated by DeLong's out of Jefferson City, Missouri, and installed by Emery Sapp & Sons. The composite steel plate girder bridge is 670 foot long with 6 spans, a very large bridge when you think of simply pushing it into place. So I don't have much more on this one to talk about because this video just, it does better than I could with words.
I remember the day we pulled up and looked at the job, I turned around and I asked Rusty and Chip, I said, you guys up for a challenge? I said, the way to do this project is build your existing bridge beside it, roll it in, and mitigate this whole river and all the flooding we have here. It overwhelms you at first because it was a bridge of considerable length and a bridge of considerable height, and the tributaries down there you're working over, all that added together would give you reason to pause.
We've built a lot of bridges, you know, so it wasn't so much erecting the bridge, but getting it from point A to point B, you know, that you know, and being it's never been done in Missouri before, and I don't know how many times it's actually been done, period, but supposedly this was the largest bridge that's ever been slid.
We had Teflon bearing pads, a stainless steel plate that went from the temporary bent all the way across to the permanent bent. We used soap as a lubricant to actually allow the Teflon to slide on top of the stainless steel. And then on each pier we had a hydraulic ram there were 7 locations. Each one was synchronized to a central unit that actually controlled the hydraulics. It would push the bridge about a 2 foot, I think, and then the ram would actually pull itself forward, and then it would fall into 2 locking keys and then push against it, and it would continue that process until it got it into its final position 40 feet away. At the end of the day, when we actually got it in final position, we had our surveyors out on the project to check at each bent location at centerline. We had already previously marked where centerline should be. They went out and verified, and when we completed the push, the most we were off was 1/4 of an inch, and the least we were was as close as a thickness of a hair.
Once we moved the bridge over, and we knew we still had to tie in the roadways, but once that bridge slid over, I mean, the feeling was, it was pretty special.
All the risks that was associated with the project actually came true. We were able to show that. We eliminated the risk and still completed the project on time with several delays involved in the process, and still were able to hit the target date that MoDOT set out.
So there was a 20-day bridge closure compared to an over 2-month closure required for traditional construction methods. This bridge weighed 2,050 tons, and the slide took 10 hours. That's quite a feat of engineering. So moving on to truss bridges. Truss bridges are a favorite of engineers and the public. Fabricators and bridge manufacturing firms can prefabricate truss modules for shipment to the site where they are erected to complete the truss. Building the truss in the shop has the benefit of quality and fit and finish. Also, the shop's ability to apply steel protective systems, such as galvanizing, metallizing, or painting, is higher quality and more economical than for field applications. So in Blaine County, Montana, there was a truss that lasted 110 years. Remarkable in itself, that finally needed replacing. That's the picture on the left. However, that's not the bridge. That bridge is already being deconstructed. That's the picture during that process. A new truss structure was chosen to avoid elevating the approach road grade and keeping the structure above the 100-year flood elevation. The fabricator was Contech Engineered Solutions out of Westchester, Ohio, and the contractor was Kopp Construction. The design, fabrication, and construction was recognized with the Best Bridge Award by the Montana Contractors Association. Demolition of the old truss and construction of the new 2-span truss with a concrete deck used approximately only 7 employees. The steel truss bridge was delivered in large segments that were bolted together and lifted into place to speed erection and installation. A 300-ton crane lifted the 2 main 148-foot trusses, and a contractor-owned 110-ton crane lifted the 2 79-foot approach trusses. This video shows the demolition of the old truss and the construction of the new truss. So there's the old truss being deconstructed. It's not continuous, it jumps around. The bridge is gone. They're starting to work on the abutments for the new trusses and the pier. There's the 300-ton crane lifting the 148-foot main trusses. They're starting to put on the decking, the stay-in-place forms for the decking so they can cast the concrete. And that bridge is ready for the concrete deck. And there you have it. One reason I like this video is the drone coverage. This is pretty high quality and cool drone footage to where they could match it. It didn't, one of the pictures wasn't closer than the other. It was pretty consistent on how they put that film together. Now, during this project, due to flooding, the contractor only had 8 days available to build the structure before the concrete deck people were going to show up to place the deck. But they made it work. The trusses were lifted into place, the floor system was built, the deck panels were installed for the concrete deck formwork. Here is a large traditional truss bridge erected with accelerated bridge construction that I would bet will last even longer than that original bridge. So for our final case study, we will be looking at a bridge built with accelerated bridge construction using what's called prefabricated elements that was to be placed in an environmentally sensitive area where conventional construction just would not work. Now, I know I'm going to mispronounce these names since I don't speak Hawaiian, but the Kiahua Arboretum in the Kiahua State Forest in Kauai, I should be able to do better on that one, Kauai, Hawaii, is home to native plants and vegetation enjoyed by locals and tourists for picnicking, swimming, hiking, biking, horseback riding. They needed a bridge to replace the troublesome low water crossing that's shown on the left here that would stop visitors from being able to cross during rain events, and a bridge that fit into the natural environment. The build site was very tight, and the owner required little disturbance in the construction. The solution was that Acro Bridge from Parsippany, New Jersey, designs and builds prefabricated individual truss elements to assemble bridge trusses in various forms. The new bridge was a 110-foot long, single-lane bridge with a protected sidewalk on one side. And then the bridge was built by Macon. The prefabricated truss elements are placed in containers and shipped to the site. For this bridge, there was a 3-man crew that put the bridge together with only hand tools. There was no construction equipment. Because of the lightweight trusses, they only needed temporary falsework in the creek to place the bridge on the abutments. The roadway decking was lightweight prefabricated units that were installed on the floor system. No heavy construction equipment was necessary. When you think about it, the reason many of us became engineers is because of Tinker Toys, and Acro has continued that passion to produce prefabricated bridge element bridges to meet bridge needs. The bridge in a garden fits the needs and the environment for this state park, and the prefabricated elements met the shipping, staging, assemblage, and erection requirements for this remote region with the tight build area. That's a beautiful picture. And with this beautiful bridge setting, we will summarize today's presentation. When this lecture started, I stated that bridge designers, fabricators, erectors, and contractors are innovative in delivering bridge projects to owners. We have seen a few accelerated bridge construction case study examples of how planning or design or choice of materials or construction methods or combinations of those have been used to greatly reduce construction time, improve work zone safety, and decrease the inconvenience to the traveling public. So that concludes Lecture 5. Lecture 5 looked at applications in accelerated bridge construction. Some of the case studies we discussed are typical design bid build projects or design build projects that use modular units and construction techniques to greatly decrease the construction time and the disruption to the public. Others were from bridge manufacturing firms that will design and deliver a bridge that can be installed quickly for accelerated bridge construction. ABC has become an important part of the bridge industry in that it reduces on-site construction time and inconvenience to the public. In our final Lecture 6, we will look at a showcase of bridge case studies that these manufacturing firms can design, build, and deliver to the bridge site. Bridge manufacturing firms use experience and economies of scale to produce high quality, beautiful, functional, and economical bridges for owners across the country. Many of the examples we will look at would certainly also qualify as accelerated bridge constructions, as we will see in Lecture 6. And of course, if you would like to find more information on steel bridges and the topics of these lectures, you are welcome to visit the website shortspansteelbridges.org.